Let's take a look at the Law of Cosines, section 5.2. So we'll start off with a starter question. What formula relates the sides of this triangle? So let's take a look at the triangle right here. And I mean, we could probably find lots of formulas that relate the sides of a triangle, but the easiest one and the one that you're most familiar with takes advantage of the fact that this is a right triangle. So we could do the hypotenuse squared, which is c, should equal a squared plus b squared. Use that dozens and dozens of times. Okay, and now a couple of thought questions. What would happen to side C if angle gamma got bigger? So let's say that side B and side A, they were set, okay, they were set lengths, and then we let angle gamma get bigger. So let's say it was out like this, okay, a little more than 90 degrees. Think about what happens to side C. Well, side C is definitely bigger than it used to be, okay? So making that angle larger changes the hypotenuse so that it's longer. And what would happen if it got smaller? So let's take angle gamma and let's make that get a little bit smaller. And of course, side C gets smaller. Well, the nice thing about that idea, and it's a pretty simple thing to understand, if we take that right angle and we make it bigger or smaller, it's going to change the size of what used to be the hypotenuse. Well, the law of cosines is just an adjustment on the Pythagorean theorem that takes that into account. It accounts for the right angle, or what used to be the right angle, getting bigger or smaller than it normally is. Now, just like the law of sines, the law of cosines works on any triangle, and here's the cool part. There's no ambiguous case. We do have to do a couple of things and check a couple of things as we go along, but here's the law of cosines. And it starts off very familiar. So it's c squared equals a squared plus b squared minus 2ab cosine of gamma. And what you want to take note of is, again, it's an adjustment on the Pythagorean theorem. So we've got all three sides of the triangle represented right here. And then we've got this cosine of gamma. Now, if you look at gamma, gamma is the angle that created this side C. So angle gamma has something to do with how big this side right here is, the side that it creates, okay? So take note of the fact that it always starts with a side and ends with the angle that created that side. Starts with a side and ends with the angle that created that side, and everything else involved in the formula involves the other two sides that aren't used. So there are a couple other forms of this. So if we were to take a look at, well, what if we started off with a squared? Well, remember, it starts with a side and ends with the angle that created that side. So this has got to be an alpha. And everything else is in terms of the other two sides. So a squared will equal b squared plus c squared. And then here's the adjustment. It's minus 2 times bc. And then if we start with b squared, if we start with side b, we're going to end with angle beta. And this is AC, a squared plus c squared, and this is also AC. So again, noting that it starts with a side and ends with the angle that creates that side. Okay? So, thought question here. Let's think about this for just a minute. Why is it a minus 2ab cosine gamma in this picture right here? Well, let's think about what would happen if gamma is 90 degrees. Well, if gamma is 90 degrees, this is going to be c squared equals a squared plus b squared. And what happens if we plug in 90 degrees right here? Well, the cosine of 90 degrees is 0, x-coordinate right there at 90 degrees. Okay, that would be 0, so this whole thing just disappears. That whole thing would just be gone. Okay? So if it is 90 degrees, the law of cosines turns into the Pythagorean theorem. Well, let's think about what happens if, let's say gamma is 120 degrees. Well, if gamma is 120 degrees, I mean, we're going to have the c squared equals a squared plus b squared. Then we're going to have minus 2 times ab, and then we'd have the cosine of 120 degrees. Well, let's think about this. If this was 120 degrees, so if we change that, we expected this to get bigger. So we would expect a squared plus b squared. We'd expect to add something, but think about what the cosine of 120 degrees is. Cosine of 120 degrees is negative 1/2. So a negative times a negative, we'd actually end up adding something. So we end up adding whatever that particular quantity happens to be. And then let's take the case if gamma changes to something less. Let's say it's 73 degrees or something weird like that. Well, it's still going to be c squared equals a squared plus b squared, but then let's think about what we've got here. We've got the 2ab, and then I've got cosine of 73 degrees. Well, 73 degrees is going to be a positive value, so I'm going to have a minus 2ab cosine 73 degrees. So whatever this is, I mean, we could figure out what it is exactly once we have numbers, but we're going to be subtracting something. So when the angle is larger than 90 degrees, we have a minus, which gives us a plus. That increases the size of angle or side C. And when gamma is less than 90, the cosine of that angle is positive, so we just have a negative times a positive, so we end up subtracting. And that's how it makes the adjustment. And then one thing that you want to be careful of in this section is they're going to give you some problems where they say, you know, do you have enough information to solve this? Do you have enough information to even make a triangle? Or does the information lead you to a triangle? And for that, we don't want to forget something called the triangle inequality. And if you've forgotten that from geometry, it says the sum of any two sides of a triangle must be greater than the third side. So if you take any two sides of a triangle, add them up, they've got to be greater than the third side. Well, the easiest way to check this is to do this. The sum of the two short sides must be longer than the third side. So you'll notice in this first example right here, it says, determine the number of triangles that can be made with the given parts. So if I've got a side of 3, a side of 5, and a side of 8, well, the triangle inequality says if I take the two short ones and add them together, it's got to be more than this right here, more than that third side, okay? Can't even be equal to it. It's got to flat be greater. So the answer there is no to that inequality. That's not a true inequality. So we couldn't make a triangle using these parts. And we could draw a diagram to figure out why. Let's take 8, the long side here. Let's put a side that's 3 units long here and a side that's 5 units long right here. And then let's kind of bring those together and try and make them meet. Well, because these would come down and touch, just barely touch right here, there's not enough to make a triangle, and that's why it's got to be strictly greater than. So let's take a look at this one. Again, grab the two short sides, 5 and 8, that's 13. Are they greater than 10? They are, so we would have a triangle. And again, we could draw a picture of what this looks like. This would be 5, this would be 8. If I try and slide those together, okay, they would come together and they would touch and make a triangle. And then let's take a look at this information right here. Might seem silly, but they do throw a couple of these at you. We've got one side and then we've got 3 angles. And then here's what we'd want to check. This doesn't have anything to do with the triangle inequality, but let's add these together. So if I have 28 and 92, that's 100, let's see, that's 120. And then if I add 70 to that, that's 190 degrees. And we know that that won't work. So we get one triangle on this one, none on this one, and none on this one right here. Okay? Now, if you take a look at in the section, it actually outlines some procedures for solving triangles based on whether it's an angle-side angle, a side-side angle, side-side-side, and so forth. Okay? But really, there's no substitute for stopping and thinking about the relationship between the sides and the angles on each one of these problems and considering drawing a picture. I mean, we're always going to draw a picture so that we can represent that. Or maybe we should say, draw a triangle to represent these. Okay? So, solve the triangle using the given information. So I've got alpha 121.3, side B 2.9, and side C 3.1. So the first thing we want to think about is we want to figure out, well, is this an angle side, angle side, a side angle, a side side, or a side angle side? So think for just a second. If this is side B and this is side C, angle alpha has to be between those. Because remember, our diagram would look something like this. It may or may not be a right triangle. But if we're given side B and side C, side A would be over here. That makes alpha in between sides B and C. So keep those things in mind. What we've got here is we've got a side, an angle, and a side. So we've got a side, and then the angle, and then the other side. So let's draw what this would look like. And again, it's good to draw these roughly to scale. So I'm going to draw a side that's 3.1 here, so that'll be side C. I'm going to draw an angle that's about 121, so about something like this. And this other side is 2.9, so it's about the same length, so 2.9. And this angle right here is 121.3. And it says solve this triangle. So what we're missing is this angle right here, and this is gamma. This is side B, so this would be beta. And since this was angle alpha, this would be side A. And that's what we're after here. So you'll notice that I need this side, but I have the angle that created that side. I don't have any corresponding angles over here to match up with 2.9 and beta and gamma and 3.1, so I can't use the law of sines. So let's try the law of cosines. So I'm looking for side A, so I'm going to do a squared equals, I'm going to write b squared plus c squared. There's the Pythagorean theorem, and then remember, it's going to be a minus 2 times these two guys right here, so 2 times bc, and then the cosine of alpha. So in this case, I've got a squared equals, let's do b squared, 2.9 quantity squared, plus 3.1 quantity squared, minus 2 times b, 2.9, c is 3.1, and then the cosine of the angle that created that side that we're looking for, 121.3. All right. So if I want to know what A is, I'm just going to take a big square root of that. So I'm going to take the square root of both sides, and I get A equals, and let's grab the calculator and have it figure this out for us. So we're going to make sure that we're in the right mode. Make sure we're in degree mode. And then we're going to come back here and we're going to do a square root. And then I'm going to do 2.9 squared. And then plus 3.1 squared, and then minus 2 times, and I'll go ahead and put the times in here, 2.9 times 3.1 times cosine of 121.3. And let's think about this for just a second. This is the largest angle on here, so we're expecting a side to be quite a bit bigger than the two of these. And let's see what we get. We get 5.23. Okay. So this is, I'll change colors here so we can see it. This is 5.23. Okay. Now, I think I've mentioned before that this textbook tends to round, in my opinion, a little bit too soon. So what I'm going to do here is, we know what side A is. Side A is 5.23. We got that taken care of. And we also need to find these angles right here. Well, there are a couple different ways to do that. If you want to use 5.2, 5.23, I suppose that's okay. Sometimes you'll look in the back of the book and the answers won't be very close to each other. So here's what we're going to do. I'm going to store that answer in A. So that was store right here above the on key, and I hit the alpha button to grab the A. So I've stored that in there. And then we want to think about this. Let's come back to our diagram here. Let's find angle beta. So in order to find angle beta, that's going to be the sine of beta. This would be one way that I could do it, over 2.9. And now because I have a corresponding angle inside, I can do the sine of 121.3 over, let's see, 5.23, or A, if I've got that stored in my calculator. So that means, let's see, this is going to be sine of beta would be equal to 2.9 sine of 121.3 over 5.23, which means beta is going to be equal to the sine inverse of all of this stuff. So 2.9 sine 121.3 over 5.23. So let's have the calculator do that also. And for that, I'm going to hit sine inverse 2.9 times the sine of 121.3, close the parentheses, and then divide that by, I could type in 5.23 and hit enter. I get 28.37 degrees. Now, if I recall the same command, and let's say that instead of putting in that decimal approximation, let's say I put in, alpha A, what I stored in there, 28.37. So we're off by, let's see, 5 thousandths. Not too bad on this particular one here. So we're going to call this one 28.37. So this angle right here is 28.37 degrees. And then, of course, I can get gamma by subtraction. I could get beta another way. I could do it this way. And this might seem a little bit silly, but in the long run, sometimes this can work out to be pretty advantageous. I know all the sides now, so if I wanted to figure out what beta was, I could do it this way. Let's start with 2.9, square that. That would be equal to, so if I've got b squared, that's going to equal a squared, 5.23 squared, plus c squared, 3.1 squared, minus 2 times 5.23, 3.1, and then the cosine of beta. Well, in order to get beta by itself, here's what we need to do. Let's move these two terms to the other side. So 2.9 squared minus 5.23 squared minus 3.1 squared. And then I'd have minus 2 times 5.23, 3.1, cosine beta. So I'm going to take everything and divide by these guys right here. So this is going to be minus 2, 5.23, 3.1. And then I just have cosine of beta over on this side. So if I take the cosine inverse of this side and the cosine inverse of this side, I should get the same answer. So let's just check and see if that works, because we might be using this a little bit later on. So I'm going to do a cosine inverse of, and then I need to make sure that I do the entire top divided by the entire bottom. So I'll start a set of parentheses, and here's what I've got. 2.9 squared minus 5.23 squared, and again I could use that stored answer that I had up above. Okay, there's the entire top, and then I'm going to divide that by the entire bottom. So we'll do negative 2 times 5.23 times 3.1. And if we did this right, well, there we go. Okay, a little bit of error because of the squaring and all that sort of stuff. So if you use a different technique, we might get a slightly different answer. To the tenths place, if we rounded, it would be the same. So we get 28.29 degrees. Okay, both of these would round to 28.3. And maybe that's why this book does that. But then you can just add 121.3, let's see, 28.37, and subtract that to figure out what gamma is. All right, let's take a look at the next one then. So here's what we've got on this one. We've got side A, we've got side B, and we've got side C. So in this case, we've got a side situation. So again, let's draw these roughly to scale. I'm going to draw the large one down here, 7.1. And then this one I'm going to label that as 6.3. And this one is 6.8. So these are all about the same. Again, let's see, 6.3, that's A, so this is alpha. 7.1, that's B, so this is beta. And C is 6.8, so this is gamma. All right. Let's go through and find this, and you'll notice that we've got to find an angle here. So we're actually stuck doing this right here, because notice if you've got all three sides, you can find an angle. So let's find alpha first. So let's do a squared, so that's going to be 6.3 squared. That should equal 7.1 squared plus 6.8 squared. Notice how they're just kind of right in order for us there. And then minus 2 times 7.1, 6.8, cosine of alpha. And again, notice what happens here. as I move these two around, I get 6.3 squared minus 7.1 squared minus 6.8 squared. And then I'm going to be dividing by this stuff right here. So that's going to be minus, whoops, that's going to be minus 2 times 7.1 times 6.8. And over here, I would have cosine of alpha. Well, in order to get alpha by itself, I'm just going to take the cosine inverse of both sides. Cosine inverse of this side as well. So this is going to give me alpha equals, and let's see what this is. And this is one reason why this is kind of nice. A lot of the problems in this section have decimals like this. So if I already have that structure in there, I can come back here and I can just edit this command. So 6.3 minus, this is 7.1. I'll delete that because I don't need that decimal place. This next one is 6.8. And then over here, we're going to have minus 2 times 7.1. Delete that again. And you'll notice that I'm replacing things in kind of a uniform fashion here. And that's going to show up again in just a second. So this is 6.8. Got everything typed in there correctly. Hit enter. And let's think about this for just a second. 53.8. This is the smallest side. This is not quite an equilateral triangle, but we should expect something here around 60, but definitely less than 60. So what we've got here is 53.8. I'm going to call it 53.9. So 53.9 degrees. Okay. Well, let's find. Yep. Let's find gamma next. So in order to find gamma, here's what we do. I could go through and say, you know what, this one is 53.9 degrees. And now I've got a side and a corresponding angle, and I could use the law of sines. I could say the sine of gamma over, let's see, 6.8. That should equal the sine of 53.9 over 6.3. And again, we're expecting something because this is a little bit bigger side. We'd be expecting an angle that's a little bit bigger than 53.9. So we could solve it that way. Or what we could do is we could run through and we could just change the order of these things. So if I did that, I'd be starting off with 6.8 squared, 7.1 squared. This would be 6.3 squared. And then 2, 7.1, 6.3, and then cosine of, instead of alpha, cosine of gamma. Well, notice how similar these are, and when I move things around, notice the only thing that I changed was 6.3 for 6.8, there's a 7.1, 6.3 for 6.8, 6.3 for 6.8. So I only changed 3 things. So what I could do is let's just figure out what gamma is by doing cosine inverse of this stuff right here, except for we're replacing a 6.8 with a 6.3. So this is 6.8, or swapping those, I should say. And then on the bottom would be a 7 and a 7, or a 2 and a 7.1 and a 6.3. And that's going to tell me what gamma is. And again, the nice thing about this is law of sines is fine if you want to use that. But let's take a quick look here. If I just recall that, all I have to do is just edit. Look how easy this is. That's an 8. That's a 3. Hop down here. And that's a 3. I make those 3 changes in there, hit enter. And look what we've got here, 60.64. So we get 60.64, okay? So this angle right here, 60.64. And that is a little bit bigger, just as we expect, and then we can use subtraction to get that one right there. It will give you the same answers if you were to do this within a decimal or 2, okay? All right, so let's take a look at the other side. We've got another navigation problem here. So Andrea and Carlos left the airport at the same time. Andrea flew 180 miles per hour on a course with a bearing of 80 degrees. Carlos flew at 240 miles per hour on a course with a bearing of 210 degrees. How far apart were they after 3 hours? So let's see here. Bearing of 80, that's slightly northeast. And then a bearing of 210, 90, 180, 210. That's slightly southwest. So let's have the airport be about right here, heading off in this direction and heading off in this direction. And let's figure out how long those sides are. Well, if this is 3 hours at 180 miles per hour, that's going to be 3 times 180. That's going to be 540 miles. And this is 3 hours at 240 miles per hour. Well, this is going to be 3 times 240. That's going to be 720 miles. And then the question is, how far apart were they? So we want to know this right here. Well, in order to figure that out, notice we don't have any angles here. So let's take a closer look at this. Remember, we had some information here that we didn't actually draw on the diagram, and they were the bearings. We kind of roughly approximated them, but this was 80 degrees. I'm going to blow this up just a little bit. If that's 80 degrees, this is 10 degrees. And we also had this bit of information that this bearing was 210 degrees altogether. So if that's 90 and 180, that means this is 30. And then we've got 90 in here. So I've got a 90-degree angle, 30 degrees over here. So this is going to be 130 degrees altogether. 130 degrees altogether. So I'll shrink this back down. And here's the diagram we're after. 130 degrees. And we're going to have lots of problems like this. 540, and this is 720. And all we want to know is this right here. Again, we can use the law of cosines because we have a side, an angle, and a side. Start with the side, end with the angle that created that side. So we're going to have x squared equals 540 squared plus 720 squared minus 2 times 540, 720, cosine of the angle, which is 130. And remember, cosine of 130 is going to be negative. That means we're going to be adding a pretty large quantity to this. And then we're going to take the square root. So x is equal to big square root. Let's see what we've got here. 540 squared plus 720 squared minus 2 times 540 times 720 and times the cosine of 130 degrees. So it looks like that's about 1144.5. 1144.5, and that would be miles apart. Okay? So almost done here. Let's take a look at the next little thought question. It says, why might you want to use the law of cosines even if the law of sines might apply? And in other words, why might the law of cosines be a little bit easier to use? So if we think about that for a minute, the nice thing about the law of cosines is there's no ambiguity. Okay? Remember, if there's a triangle, the law of cosines is going to get the answer for us. And the other thing is, when we're finding angles, remember, when you use the sine inverse, it only has a range from negative 90 to 90. And negative angles certainly wouldn't work on a triangle. So really, the only effective angles that we could use using sine inverse would be from 0 to 90, the acute angles. But the law of cosines, if you're trying to find an angle, it will give you the angle even if it's obtuse. So there are some big advantages to using the law of cosines, and you might want to think about those. And like here, a lot of people will do this problem this way. But consider doing a couple of them this way, because really all you had to do is recall that command right here and edit 3 little numbers and hit enter, rather than setting this up and all that sort of stuff. So it's probably 6s either way, but it's important to think about why we might want to use the law of cosines more than the law of sines. But they do both have very good applications. And this is example 5 in the textbook. or at least the setup for example 5, and it comes, this formula that for the length of a chord comes from the law of cosines. So we just want to take a look at this. This is a chord right here. It touches two sides of the circle. And the circle has a radius right here and a radius right here. And then we've got the central angle alpha. So if we just ignored the circle and just focused on this triangle right here, the length of this side should have something to do with that central angle right there, the side that created it. And we can use the law of cosines in order to figure out the length of this right here. Like let's say we knew this side right here, we knew the radius over here, and we knew the radius here, and we knew this angle right here. Well, what we can do is we can say, well, this side length right here should have something to do with the angle that created it and the Pythagorean theorem. So start with the side, end with the angle that created that side, and the other two sides are just r here and r here, so we'd square each one of those. These are both r. So we have r squared and r squared, that's 2r squared. And then I have minus 2r squared cosine alpha. And then notice that because these have the same, we can factor out an r squared is what I'm after there. And then we can just take the square root of both sides. So if I take the square root of both sides, I get an a here, and it would have to be positive. We don't have to worry about the plus or minus. And then the reason I didn't take the 2 out is because we're not going to be able to simplify that using a radical anyways. But radical r squared is r, and then I have the radical of 2 minus 2 cosine alpha. So the way this theorem is stated is if a chord of length a subtends a central angle alpha in a circle of radius r, then you can find the chord length based on the central angle and the radius. And then we'll just use this formula. It says if each side of a regular octagon is 12 inches long, what is the distance from the vertex to the center? So an octagon, we've got a stop sign thing going here, and then that is inside a circle. So it looks something like this, okay? Crappy looking, but let's blow this up and take a good look. What it's asking is, if this side right here, the side of the octagon is 12 inches, it wants to know what's the distance from a vertex, a corner, to this right here. It wants to know what the radius is. So we can use that and this formula right here to figure out what the distance is. But let's see, let me make this a little bit smaller. They didn't give us the angle, so we're missing this angle right there. Well, let's stop and think about this. This is a regular octagon. So if I were to take this and divide it up like that, I've got 8 pi pieces, if you will, there. This angle right here would be half of a quarter of a circle, or half of 90 degrees. Or we could take 360 and divide it by 8. We're going to get 45 degrees. So to solve this, I've got A is equal to 12. That's the chord length. I don't know what R is, but I do know the central angle is 45 degrees. So let's plug these pieces in. So this is going to be 12 equals R square root 2 minus 2 cosine of 45 degrees. So that means R is equal to 12 over square root 2 minus 2 cosine 45 degrees. Make sure your calculator's in degree mode. Type that in and you'll have the answer. Let's go ahead and do that really quickly then. Let's clear that off. And let's see, we've got 12 divided by square root 2 minus 2 cosine 45. Close the parentheses there. 15.67. So that radius, 15.67 inches. Not sure, haven't looked really closely at a stop sign, but that sounds about right. Some of those are pretty good size. So hopefully that helps and you're on your way with the homework. Thank you very much.